Welcome. In this session in linear data analysis, we'll explore the scatter matrix that's based on observations rather than on variables. To do this, we'll first get a preliminary result, which is we'll re-express our matrix that has zero mean data. We begin with data, and these are all real numbers, and there are m observations, and there are n variables. And what we did first was we computed a row-like object, which was the mean of these. And we computed that as the mean of the data was we could take the ones vector and take that ones vector and transpose it, and we could multiply that by our matrix A. And what that would do is that would compute the sum of each of the rows. And if we then divide that by the number of observations, this row-like object will contain the mean of column 1, column 2, column 3, and so on through column n. We would then form our zero mean matrix, and we said that we would take our data and then we would subtract. We would take the ones vector and multiply it by this row-like object. So this, let's recall, is going to be a rank 1 matrix. So this will be, what this will look like is this will copy the row-like object into 1, 2, 3, and so on until we've completed all of the observations. And then we take our original data and then we subtract this and we get our zero mean matrix. Well, we can now factor this. So we can write that. If we want to factor this out, first thing is let's expand this term. So that will be a minus, and then I'll pull this out first. That'll be 1 over m times the ones vector times the ones vector transpose times our data matrix. And I can now say, oh, well, that I can factor as that would be the identity matrix minus this amount minus 1 over m times the ones vector transposed and multiplied by our A. So what I can do is I can now see that when we were creating our zero mean data, what we were doing was we were multiplying by an m by m matrix, and it turns out that this is rank m minus 1. And let's write that. We were using the vector symbol G to indicate a centroid of data. Let's use a capital G with a subscript of m to be the m by m version of this matrix times A. Let's leave that aside, and now let's revisit principal components analysis. So in PCA, we used a scatter matrix, and we wrote that as M transpose M. And I'm going to have two scatter matrices in this session. So I'm going to put a subscript of V. We can think of that as, for now, as variables. And we can use the singular value decomposition to write M as an orthogonal matrix U, a singular value matrix sigma, and an orthogonal matrix V transpose. I can then rewrite S sub V. I rewrite the variable style scatter matrix. So that means that the variable style scatter matrix is, so when I do that transpose, what I get is that will be V transpose, so that V transpose is V times sigma transpose times, and then I would get U transpose U, but that's the identity, so I can omit that, times the sigma for this times the transpose. And the spectral decomposition is that we would write that as V, and then the eigenvalue matrix, so it's a diagonal matrix, and let's put a subscript of V on that, times the transpose. So we can use the singular value decomposition, or we can use the spectral decomposition directly. We would then write the scores as, so the way we wrote that is we called them scores, and now let's subscript it with a V, and we said that that was the zero mean data times the eigenvectors of the variable style scatter matrix. So that was M times V. But now if we compute, if the scatter style matrix is this, then when we do M times V, what we get is that will be U times sigma times V transpose times V, which is the identity. So we have this, and that has to equal the left the left orthogonal singular vectors of the zero mean data times, another way to write sigma is that is the square root of the eigenvalues derived from the variable style scatter. So now let's do this. Let's consider writing this in the other way. So let's say that we'll call the U style or observation style scatter. Let's say that that is our zero mean matrix, and then we'll put the transpose on the right. And if we use the singular value decomposition, we can see that M will be U times sigma times V transpose, and then when I do M transpose, that will go over to be V, and V transpose times V is the identity, so that's eliminated, times sigma transpose times U transpose. And we can write that as the U matrix times the eigenvalues of the U style times U transpose. Now, let's recall the Svd derivation. And that is that if the rank of our zero mean matrix equals R, that implies that the first R eigenvalues in the variable style, that's in the variable style and the observation style, are equal. So let's put a little exclamation mark. We don't usually do that. That means that we can write the scores that come from our observation style. We would say that that is now going to be, that has to be equal to the scores that we get from the variable style. So that has to be equal to U times the square root of the eigenvalues that we get from the U style. And so these have to be the same. It doesn't matter whether we use the variable style scatter matrix or the observation style scatter matrix. Because those scatter matrices, the first R eigenvalues are the same, the scores that we get have to be the same. Now, what's the difference in them? Well, the difference is whatever is left after the rank is that if our data up here are tall and thin, which happens when the number of observations greatly exceeds the number of variables, in that case, this will be a much larger matrix than this. This will be n by n, the number of variables. This will be m by m, the number of observations. So that means that this eigenvalue matrix and this eigenvalue matrix, the first R of them, up to the rank, they'll all be the same, but this one is going to have a whole lot more zeros than this one does. And that will be the difference. So now, how can we rewrite this? Well, let's expand this just a little bit. That SU, we said, is MM transpose. But now from this result, that has to equal our centering matrix times our data matrix times the transpose of our data matrix times our centering matrix transposed. That is, it has to be this observation style scatter matrix can be written in these terms. And we'll note incidentally that by construction this centering matrix is symmetric, positive, semi-definite. And so we can write the observation style scatter matrix in terms of the data times the data transpose.